Morning folks, the phone's starting to play up a wee bit, so when I was recording this, it all deleted. Another heartbreaking story, but anyway, we'll try and chat you through it and what way I was doing it. So we're discussing bonding, and there's two types of bonding. There's ionic bonding and there's covalent bonding. So ionic bonding is when there's a transfer of electrons. It's between elements on the left hand side of the periodic table, the elements on the right hand side of the periodic table, and that is essentially your metals, like your group 1 or your group 2, and your non-metals, say your group 6 and group 7. Now you have looked at electronegativity difference. That means there's a separation of charge, and there's a complete separation of charge in these. So the electronegativity difference is bigger than 1.7. And a famous example, sodium chloride, magnesium chloride. I always think of my alkali or alkaline metals with my halogens, say, or my group 6. Covalent bonding then is when they share electrons. So there's two types of covalent bond. They can share them equally or they can share them unequally. So when they share them equally, it's known as a non-polar or a pure covalent bond. So it's like H2O2, your hydrocarbons are also non-polar. Your electronegativity difference of those is very small, and the shapes of them as well contribute to your hydrocarbons. So your alkanes, alkenes and alkynes being non-polar. And phosphine is a famous example, even though phosphine we'll see has a pyramidal shape, and we'll chat how that should be a polar molecule. It is non-polar, as your electronegativity difference in it has 0.01 or something very small. Whereas polar covalent bonds, they share electrons, but they share them unequally. Some electrons move closer in particular bonds to another. So say we look at NH3 and one of those nitrogen-hydrogen bonds, your electrons might move slightly closer to your nitrogen, and this becomes slightly negative, while your hydrogen becomes slightly positive. It creates what's known as a dipole, a separation of charge. So think of the ones maybe with your dipole-dipole bond and your hydrogen bonding. That's your intermolecular forces between your bonding. And the electronegativity difference here is somewhere between, say, 0.3 and 1.7, less than 1.7, that's polar covalent. Now we'll look at the shapes of covalent molecules. Ionic compounds result in crystal lattices. So your high melting and boiling points, solids at room temperature, don't conduct electricity in a solid state, but when they're molten or in aqueous solution, they conduct electricity as the ions are free to move and carry the charge. Covalent molecules, opposite properties. So learn the properties of ionic compounds. These are just going to be the opposite. So they share the electrons. So we look at the simplest type, say hydrogen, H2. Doesn't satisfy the octet rule. We'll see there's a few exceptions to these, especially in the early stages of our shapes of covalent molecules. Hydrogen share one pair of electrons. You can either draw it like this or this. This represents your single covalent bond. They are my electrons. Hydrogen. Each hydrogen atom has one electron each. And when we get a shape here, we get a linear shape, because according to the vsepr theory, the electrons end up as far apart as geometrically possible. This is non-polar as well. I always think anything with bond pairs only, pairs of electrons involved in bonding. There's my bond pair there. Anything with bond pairs is non-polar. So any of the nice shapes, your linear, your trigonal planar, your tetrahedral, is non-polar, as the center positive charge coincides with center negative charge, and we'll discuss that later on. In our BCl2, we have the bonding that looks like this. So each beryllium has 2 electrons. Chlorine wants a share of one of these electrons to satisfy the octet rule. So either or, I nearly prefer this method, but you can see there are your 2 single covalent bonds. If they ask you to account for the shape, you have to go through this spiel. It's got 2 bond pairs, 0 lone pairs on the central atom. It's always on the central atom. So there we go, beryllium's our central atom. So it's got 2 bond pairs, 0 lone pairs. Any molecule, 2 bond pairs, 0 lone pairs, is always going to be linear. So there's the shape then. of our linear molecule. Again, we can see these chlorine atoms ending up as far apart as geometrically possible, 180 degrees away from each other, according to this theory. Now, they'll ask you sometimes, how can a molecule be with polar bonds be non-polar overall? So what they mean by polar bonds, they'd be looking at something like this. There's one of my polar bonds. That single bond there. Be non-polar overall. Now what you've got to look at there is electronegativity. And we see there beryllium had electronegativity of 1.5, while chlorine was 3. So this is a bigger electronegativity. So there's a bigger pull for these electrons. So they're going to move slightly closer towards these chlorines. And when they move slightly closer towards these chlorines, they get these negative charges closer to it, and it becomes slightly negative. So these wee individual bonds, that slightly is just a sigma, an unfinished state, becomes slightly negative, while your beryllium, since it loses the electrons, becomes slightly positive. So the individual bonds are polar, that's all okay. Now the molecule is non-polar. The reason for that is, if I asked you where the centre of positive charge is, you'd say the beryllium, because it's the only place where the positive charge is. If I asked you where the centre of negative charge would be, you'd say, oh, it's on the beryllium atom as well, because it's halfway between the two chlorine atoms. Yeah, it's halfway between the two. Now, we'll do another shape here, BCl3, and then we can give you a few leaving cert questions on this. BCl3, if you're looking at the bonding on it, you can have it like this, or you could have it like B is 3 electrons, 1, 2, 3, chlorine is 7, wants a share of 1. There's the other chlorine atom. And that's not the shape of it, but that's going to account for the shape. Now when you're accounting for the shape on that central atom, my beryllium there, I have 3 bond pairs, 0 lone pairs. Anything, any molecule, 3 bond pairs, 0 lone pairs is trigonal planar, or you might say triangular planar. Planar just means flat on a page. Since it's flat on a page, 180 degree or 120 degrees apart from each other, that many squiggles in then from before. So now if we're going to look at the individual bonds, chlorine has a value of 3, boron has a value of 2, bigger value, more electronegative, bigger pull for the electrons, each of your chlorines becomes slightly negative. So if we're looking at an individual bond, the chlorine becomes slightly negative, your boron becomes slightly positive. Now if I ask you for the centre of positive charge, again you'd say it's on that boron atom, which only is the boron atom with the positive charge. And if I ask you for the centre of negative charge, you'd also say the boron atom. So the same scenario, the centre of positive charge and the centre of negative charge coincides, therefore the molecule is non-polar, even though the individual bonds are polar. You know, so anything with bond pairs is non-polar, so insoluble in water. Next one here, tetrahedral. We're looking at CH4 or SiH4. You're looking with one electron and one with 4 electrons, valency of 1 and a valency of 4. So carbon, 4 electrons in its outer shell, hydrogen, each with 1. So 4 single covalent bonds. According to the vsepr theory on that central atom, 4 bond pairs, 0 lone pairs on central atom. That's accounting for the shape. If they ever ask you to account for the shape, you have to mention this and this on the central atom. Therefore the shape is tetrahedral. Now, is it polar or non-polar? Instantly I know it's no lone pairs, so it's non-polar. But to discuss it, individual bonds, say we take this wee individual bond, carbon and hydrogen, that's the actual shape of it, by the way. 2 flat on the page, 1 going away from you, 1 coming out from you, your wedge and your dashed line, doesn't matter where you put those. Bond angle here, not the nicest, 109.5, but remember that, because every time we lose a bond now, it's going to get 2.5 degrees smaller, and I think this is like a radio, 109.5 FM, you know, so remember that, and then just get 2.5 degrees smaller for the remaining 2 shapes. So we're looking at individual bonds. Carbon value of 2.5, hydrogen value of 2.1. So slight difference, very small difference. But anyway, there is a small difference. So carbon, slightly bigger value, stronger, so it pulls the electrons closer to it. Pulls the electrons closer to it, becomes slightly negative. Your hydrogen loses those negative charges, becomes slightly positive. Again, if I ask you for the center of negative charge, you'd say the carbon atom. Center of positive charge is also on the carbon atom. That's just like a pyramidal shape with one above it. If I had my shape, I'd show them to you. But take it from me, it's also on the carbon atom. So again, your center of positive charge coincides with your center of negative charge, therefore it's non-polar. And that's CH4, that's a hydrocarbon. Hydrocarbons are all non-polar. So your alkanes, alkynes, your aromatic compounds, which is benzene only, are all non-polar because your electronegativity difference is very small, and with your tetrahedral shape as well, so insoluble in water. And your last two shapes, now we're looking at ones with lone pairs. Lone pairs just make it a wee bit different. So there's ammonia. Ammonia, you've got on that central atom 3 bond pairs. There's me 3 bond pairs, and this is known as a lone pair. So 3 bond pairs, 1 lone pair. Anything with 3 bond pairs, 1 lone pair has a pyramidal shape. If you're looking at individual bonds now, your electronegativity of nitrogen is 3, hydrogen is 2.1. Bigger value, bigger pull of the electron, pulls the electrons closer to it, becomes slightly negative. Your hydrogen, slightly positive. Now, since it has a pyramidal shape, oh yeah, and when you're drawing your shape, don't forget to put in your little ears. Those little ears are just my lone pairs. And what they do is force these bond angles closer together. So if they ask you to account for the bond angle specifically, you've got to say that lone pair repulsion is greater than lone pair repulsion, which is greater than bond pair repulsion, which forces the bond angles closer together. Anyway, going back to symmetry and polarity, your center of negative charge is on the nitrogen atom. Your center of positive charge, now if it's pyramidal shape, is going to be somewhere in the bottom of the base of the pyramid. So they don't coincide, therefore it's polar. So if they don't coincide, it's polar. So it's soluble in like water, insoluble in cyclohexane. And another thing, your bond angle, as I said, it's almost just like you removed this here and it's become 2.5 degrees smaller. Always 2.5 degrees smaller. I'll show you the next one, 2.5 degrees smaller when you remove another bond. Your last one, there's water. Water, 2 bond pairs, 2 lone pairs in your central atom. Anything with 2 bond pairs, 2 lone pairs in the central atom is always V-shaped, or this new word I learned, bent, for describing shapes. When you're drawing it then, like so, don't forget your little ears at the top, forcing them bond angles down, closer together, and your bond angle is 104.5, 2.5 degrees smaller again. Looking at individual bonds, bigger value your oxygen, bigger pull for the electrons, slightly negative, while your hydrogens are slightly positive. They're my individual bonds. So the individual bonds are polar. Is the molecule polar? Center of negative charge is on the oxygen, center of positive charge somewhere here. They don't coincide, they don't cancel each other out, therefore the molecule is polar, and that's it. I'll get you a few leading cert questions now soon, but in case this phone gives up, all the best.